Hi, and welcome back to Codex. Our talks this summer feature graduate students and postdocs who were nominated to speak by their senior colleagues. Today we have Chad Berner, who is a PhD student at Iowa State. We're happy to have him here today to tell us about frame-like Fourier expansions for finite Borel measures. Take it away, Chad.
Okay. Thank you all for coming, and thank you to the Codex coordinators for the invitation. So as was said, I'm going to talk about frame-like Fourier expansions for finite Borel measures. So to kind of give you a roadmap of where we're headed here, so first we'll talk a little bit about the history of Fourier frames and some of the famous problems there. In the next section, we'll define what I mean by frame-like Fourier expansions. I'll give some examples of measures that have frame-like Fourier expansions and measures that don't. And then in the next section, we'll dig into a more specific case of frame-like Fourier expansions whose coefficients come from operator orbits. And then finally, in the last section, I'll talk about a general necessity result for Fourier expansions to kind of illustrate an overall feel with what's happening with these type of expansions. So first of all, try to set the stage here a little bit with Fourier frames. So we're all familiar with Lebesgue measure on 0, 1. We have an orthonormal basis of exponential functions. And because of this, we can write all elements in our L2 space as Fourier expansions with coefficients against these orthonormal bases, which is very useful in Fourier analysis theory. And so a natural question that many mathematicians have studied is, what about other measures? Can there be other finite Borel measures on 0, 1 that have an orthonormal basis of exponential functions? Because other measures are important for other areas of approximation as well. And if they have an orthonormal basis of exponential functions, they can have a similar nice Fourier expansion for elements of their L2 space. And so some of the interesting work on this problem that I want to share first is work due to Jorgensen and Pedersen, which says there's a positive result for a measure on the Cantor-4 set. So the Cantor-4 set is an analogy for the Cantor set where we take base 4 expansions and we only allow for digits of 0 and 2. So that's the Cantor-4 set. There's some open intervals generating the Cantor-4 set, and we can define a uniform Lebesgue measure on these sets, and then we can take a limiting measure, and we get this uniform measure on the Cantor-4 set. And yes, the result is that this has an orthonormal basis of exponential functions. So we have nice Fourier expansions with a measure like this. But even more interesting, I think, is that they showed that if you take the uniform measure on the regular old Cantor set, this can't have an orthonormal basis of exponential functions. And it's even stronger than that. They even showed that if you have 3 distinct exponential functions on the uniform measure on the Cantor set, that they cannot be orthogonal. So the answer to the classic question on the previous slide is absolutely not. And this is a counterexample of a measure that does not have an orthogonal basis of exponential functions. But another thing a lot of us know about an orthonormal basis is it's a very strict and rigid property for a set of vectors to have. And it's often not very useful in a lot of contexts. And so it's often more helpful to get something called a frame, which is a relaxing of an orthonormal basis. And it's a lot more robust and can be a lot more useful in a lot of places, such as signal recovery. So let me put here the definition of a frame of exponential functions in an L2 space, because that's the context we're going to be working in here. So a sequence of exponentials in an L2 space is called a frame if we take inner products with any f, and we take the L2 norm squared, and we have this uniform upper and lower bound against the norm of f here. Then the exponentials are called a frame. This equality clearly happens in the case of an orthonormal basis. We actually have equality, and both a and b are 1. This is known as Parsifal's identity. So why do we want a frame of exponentials? Well, if we have a frame of exponentials, there's a sequence G sub n often called a dual frame, where we have all elements of our L2 space can be written as a nice Fourier expansion with coefficients against this dual frame G sub n. So we have these nice Fourier expansions in the case of a frame. And in often a lot of cases, this G sub n sequence may not be the same as the original sequence, but it's pretty often easy to compute anyway. Okay, so naturally, the natural question about measures having an orthonormal basis got relaxed. And a question that many brilliant mathematicians, of course, not including me, have worked on is, okay, if I can't have an orthonormal basis, can my measure at least have a frame of exponential functions so that I can have these nice Fourier expansions? And unfortunately, there's this result due to He, which says, unfortunately, that's not the case for all measures either. So their result says that if mu has a frame of exponential functions, then mu must either be absolutely continuous or singular. It must be either one or the other. So in particular, if your measure has an absolutely continuous and a singular part, it cannot have a frame of exponential functions. Okay, so the answer to this classic question is also no. Okay, so let me remind us what we mean by absolutely continuous and singular here. So an absolutely continuous measure is just a measure that's Lebesgue measure with a weight f. So I take my set A and I integrate it against this weight f and Lebesgue measure. And for shorthand, I'm going to write mu as f dx, and I'm going to call f the radon-Nikodym derivative of mu sometimes in this talk. And then sort of the opposite camp here, we have singular measures. So a singular measure is a measure that's supported on a Lebesgue measure zero set. So in other words, the only set that this measure cares about is sets that come from a set of Lebesgue measure zero. So outside of this Lebesgue measure zero set, the sets are all have measure zero. So I realize that absolutely continuous measures may be a bit easier to wrap your head around than singular measures. So let me try to kind of illustrate some examples of what these singular measures look like. Okay, so if I have a sequence of point masses, these are called discrete measures. So I have a sequence of points a sub k. What my measure does is you give it a set A, and it's just going to check if these a sub k are in the set A. And if they are, it's going to add weight b sub k. If not, it's going to do nothing. So all of the set that this measure cares about comes from a countable set a sub k, which clearly has measure zero. So measures like this are singular. And then, of course, we talked about these uniform measures on Cantor sets, which are basically by definition singular, because all of the sets that this measure cares about are subsets of the Cantor set, which we all know have Lebesgue measure zero. So hopefully that illustrates a little bit more what we mean with singular measures here. So again, we just saw that if I have a Fourier frame, I'm in one of two camps. I'm either absolutely continuous or singular. And what this neat result by Lai and Chung Kit says that we actually have a complete classification of Fourier frames for the absolutely continuous case. So it says that if my measure is absolutely continuous and it has a frame of exponential functions, if and only if my weight f is bounded above and below on its support. So as you may imagine, one of the directions of this theorem is much easier than the other. You'd be right. It's easy to show that if your weight f is bounded above and below on its support, then you have a frame of exponential functions. But this result is interesting because it says the opposite direction. It says that if you have a frame of exponential functions, this is the only way to do it, to have your weight bounded above and below on its support. Okay, and then naturally, we say, okay, what about the other case? Do we know exactly which singular measures possess Fourier frames? And the answer is no. There are many brilliant mathematicians, again, of course, not including myself, that are studying this problem, and it is still open. So hopefully that gives you some kind of background with what we mean by Fourier frames. and how we can have these nice Fourier approximations in this setting. So now we can talk about the meat of the talk, which is what do we mean by frame-like Fourier expansions here. So the first result that I want to show is a result that I think is really remarkable here. It's a result due to my advisor, Eric Weber, and one of his students, John Herr, which says that, okay, we may not know exactly what singular measures have Fourier frames, but what we do know is that all singular measures have frame-like expansions. So what I mean is all elements in my L2 space, if I have a singular measure, can be written as a Fourier expansion with inner products against a tight frame. If you know what a tight frame is, this is a tight frame, and that's great. If not, don't worry too much about it. But what's happening here that I think is really remarkable is that in the case that mu is singular, the exponentials are never a frame, but they reproduce every element in the L2 space as if they were one. So it appears the G sub n's here are a true dual frame here, but that's actually not the case. And these expansions are actually always strictly frame-like, and they're never true Fourier frame expansions. Okay. So the main question I want to discuss for a majority of the talk, for sure at least this section, is okay, if all singular measures can have frame-like expansions, at least can I have all measures have Fourier expansions with convergence in norm? And I'll ask that my coefficients be square summable because that's very reasonable. It happens in all the nice cases. And why is the title of this talk called frame-like? Well, I also want the coefficients to come from a G sub n sequence. I want them to come from inner products with a G sub n sequence. I can do this with singular measures. Can I do this with all measures? And I'll give you a spoiler, even the answer to this is unfortunately no. So we can't even have this really weak notion of Fourier frames. We can't even have these Fourier frame-like expansions. And I'll try to illustrate with a couple of results why that is not, why we can't have this, why this is not the case, that we can always have this. So the first result here is that there are even absolutely continuous measures where every element cannot be written as a Fourier expansion, let alone a frame-like Fourier expansion. So I'll kind of share what's going on with this argument here, but it's kind of maybe weird is not the right word, but maybe kind of weird where this function f we know exists, and you can even construct it. It's a continuous function whose Fourier series is unbounded. So what I mean is the classic Fourier sequence is unbounded in L infinity. We know this exists, and we can even construct one. But what this argument says is that there exists a absolutely continuous measure where this function f can't be written as a Fourier expansion. So the function is kind of constructed in this argument, but the measure is not. So let me kind of try to illustrate what's going on here. So, right, I'll take this function f, whose classic Fourier sequence is unbounded in L infinity. So by the principle of uniform boundedness, there better be a g in L1 so that this integral sequence is unbounded. So I know this g exists is basically all I know, and so that's how I'm going to define my measure. So I want my weight g to be non-negative, and for the sake of this argument, it'll be a lot easier if my weight is bounded below, so I'm going to add 1 to it as well. So this is how I'm going to define my measure. Okay, so let's say I have a Fourier series converging to this function in norm. So as we talked about, an orthonormal basis is a really rigid and not very forgiving. Maybe that's not the right word, but it's a very rigid structure where if I have an orthonormal basis sequence and it's converging to something in my Hilbert space, I don't really get to choose the coefficients. They're kind of inherently chosen for me because of the rigidity of an orthonormal basis. So it's not too bad a check. Maybe an easy exercise to the reader is that this exponential sequence with this weight 1 over square root of 1 plus absolute value of g, this is an orthonormal basis in this L2 space. And so it's not too bad to show, because of the rigidity of this, that if I have a Fourier series converging to f in norm, I had to have used the classic Fourier sequence. Well, if I have convergence of the classic Fourier sequence, it better be, the L2 norms better be bounded in norm. But that's a contradiction, because in line 1, I assumed this sequence was unbounded. In line 4, clearly this sequence can't be bounded if the sequence in line 1 is unbounded. So I have a contradiction. Okay, so can't have Fourier expansions for this function f here. So I realized that example was a little bit abstract and maybe a little hard to wrap your head around. So I'll actually give another much easier down-to-earth example where I still cannot have even Fourier expansions for elements of my L2 space. So we'll take a pretty easy example here. So my measure is going to be Lebesgue measure and a point mass. So what I mean is, you give me a set A and I'll calculate the Lebesgue measure, and then my point mass will check to see if my point is in my set. If it is, it'll add 1. Otherwise, it'll do nothing. So that's what my measure does. This is a perfectly fine measure. And I can even tell you which function cannot be written as a Fourier expansion with respect to this measure. So if I take the function that's 0 everywhere, except it's 1 at s, okay, remember, this is not the 0 function as far as this measure is concerned, because I have a point mass now. But what's happening here is my Lebesgue measure part thinks this is the 0 function, and my point mass part thinks this is the 1 function, because my point mass only sees what the function is doing at this point mass at s. So you might imagine this is going to cause problems for writing this function as a Fourier expansion. Because if I could write this function as a Fourier expansion, right, I'm summing these two measures together, so I better have convergence in each of the measures separately. Okay, so I'm going to need this expansion to converge to my function Lebesgue measure. Well, Lebesgue measure thinks this is the 0 function, so I'm going to need this expansion to converge to 0 in Lebesgue measure. So, of course, by orthogonality, all my coefficients will have to be 0. And of course, I'm kind of already hosed now, because I would be saying if the 0 sequence would converge to 1 in the singular part. So, right, the singular and the absolutely continuous part of this measure are sort of really disagreeing about what this function looks like, and they're not going to agree on what to make a Fourier expansion for this function here. And you might think about that example and you say, okay, it'd be fine if the Lebesgue measure part and the point mass part had some space. And that's exactly what I'm trying to illustrate with this second kind of toy example here. Is, let's say my point mass was a little bit more to the left here. Let's say it's at 1/4, and my Lebesgue measure part was, cut off from 0 to 1/2. So I just take integrals from 1/2 to 1. So this is a perfectly fine measure. And for this case, I will have no problems with Fourier expansions, and I can even do frame-like Fourier expansions. And I think I can try to illustrate that here with this picture rather easily. Okay, so you pick your favorite function in this L2 space, and that is drawn here in red. So basically what you picked was some function from 1/2 to 1, and then a point mass modulo some Lebesgue measure 0 sets. But otherwise, this function is, that's all this function is, because the measure is blind to this function otherwise. So what I'll do is I'll define a function g that's defined everywhere from 0 to 1. We'll have it be a step function here that takes the value from f of 1/4 here, vanishes, and then agrees with my function here on the right. And you can see that since the point mass and the Lebesgue measure part are separated here, it allowed me to have my function to vanish here, and that's going to help me with my Fourier expansion here. So what these poorly drawn purple squiggles are the illustration of the classic Fourier sums of G here. So I apply my classic Fourier sums theory, and I say, okay, I have L2 convergence with my blue function g, and because I'm taking the Fourier expansion of a locally constant function, I have pointwise convergence on the interior, so my point mass part of my measure is happy as well, and so I'll have convergence of the partial sums of g to f in norm, and I can even turn these coefficients into mu world, and I'll have frame-like Fourier expansions. Okay. So hopefully that kind of illustrates kind of what's going on here, but I'll try to say here with this main result what's overall going on here with these frame-like expansions. So I have a general Borel measure, I have an absolutely continuous and a singular part. I'll say the weight for the absolutely continuous part is h. We'll say it's bounded above and below on its support so that it's kind of nice. And then I want my absolutely continuous and my singular part to be separated. So I won't formally say what that is here, but hopefully you can see with that toy example that I want the singular part and the absolutely continuous part to have some space on their support is the idea here. And then if that's the case, all of my elements of my L2 space can be written as a Fourier expansion with coefficients against the sequence G sub n, and they even have an upper frame bound. Okay, so even though my measure in this case does not have to be absolutely continuous or strictly singular, it can have both parts, I can still have these frame-like Fourier expansions, even though I may not have true Fourier frame expansions. Okay, so it appears the exponentials are a frame. They're reproducing like a frame, but in almost all of these cases, they're not. Okay. And the other, sort of conversely, what I tried to illustrate with the other toy example is that if the absolutely continuous part and the singular part of my measure are too intertwined, I'm not going to be able to have frame-like expansions. So here's the general result here, which says that if I have a Lebesgue measure zero set of mu positive measure and it's properly contained in the support of my absolutely continuous part, again, I won't say what that really means, but again, hopefully you can see with that picture that the supports are really intertwined is the intuition here. In particular, I can't write indicator B as any type of Fourier expansion. And again, the intuition is that my absolutely continuous part of my measure thinks this is the zero function, and my singular part thinks this is the, a constant function or the one function. And so because they're so intertwined, they're not going to agree about what this function looks like, and I'm not going to be able to write it as a Fourier expansion. Okay, so something you might be wondering is why bother with Fourier frames at all? Am I trying to propose that the definition of Fourier frames is sort of, too strong and unnecessary? Well, not really, I guess is the answer, because what I try to illustrate with this slide here is that there is definitely a price you pay for doing frame-like expansions versus true Fourier frame expansions. So the first row here is basically the definition of frame-like expansions. I have Fourier expansions with inner products against a sequence G sub n here. Okay. And the second column here is about kind of a dual frame property. So if you know a lot about frame theory, you know that there are these operators called the analysis operator and the synthesis operator, where if I compose the right two of these operators, I get the identity. That's essentially what a dual frame is. And what's nice about frame expansions is I can flip the sequences. I can put one inside the inner product and one on the outside, because essentially I'm taking an adjoint calculation. But with these frame-like expansions, I'm not proposing that these operators are bounded anymore. In particular, we're not assuming the exponentials are what's called a Bessel sequence. And so I'm not proposing we can flip the sequences here with row 2. Another nice property about Fourier frames is that these series converge unconditionally. So you don't just have to take the limit on these partial sums, you can actually take the limit on z any way you want. But again, we're not proposing you can do that with frame-like expansions. So it is a weakening. We get more measures with these frame-like expansions, but there is indeed a price you pay for going from Fourier frame expansions to frame-like expansions.
Chad, can I just ask a quick question? Could you go back? I just want to clarify. So where you have red X's, you don't necessarily mean that always fails. You just mean there's no, it could possibly fail. You don't guarantee that it.
That's right. I'm not guaranteeing that happens. That's exactly right.
Okay, thank you.
Good question. But the main takeaway I want you to get from this section of the talk is that, again, if the absolutely continuous and singular part of my measure are too close, they're going to fight about what elements of this L2 space look like, and I'm not going to be able to have Fourier expansions, hence the fighting kids. But if my absolutely continuous and singular part of my measure are separated, they give each other some space, then I can have frame-like Fourier expansions. So that's the overall feel of what's going on here. And then lastly, I want to mention that you may be imagining these two cases probably don't union, and you'd be right. So what if my absolutely continuous and singular part of my measure are sort of kind of intertwined, but not too much? Can I have, any type of Fourier expansions? And the answer to that question is the title of the slide. I'm not sure, and it's something I'm still working on. But if anybody has any ideas, I'd love to hear them. Okay. So for the next section of the talk, like I said, I want to dig into a more specific case about what if I know my measure has frame-like expansions, but I also know more about the expansions. I know about the coefficients. In this case, we're going to talk about the coefficients coming from operator orbits. So what do I mean by that here? So let's take a measure that's basically a Lebesgue measure. What do I mean? I mean that it's absolutely continuous and the weight is bounded above and below. So the norms of these two L2 spaces are equivalent because the weight is bounded above and below. Okay. And because convergence in these spaces is equivalent, I know that every element in my L2 space with one of these measures can be written as a classic Fourier expansion because convergence is equivalent. And then if I want to put this expansion into mu world, I can just take my exponentials and divide by my weight g. But what I want to point out here is in these frame-like expansions, these are actually Fourier expansions. These are really nice expansions. But what I want to point out here is that both these sequences are operator orbits. So I take a vector, and I iteratively apply a operator over and over again. Right? I said some operator here, but in this case, the operator is multiplication by the exponentials. But again, what I want to point out here is that in this case, both sequences come from operator orbits. So the main question I want to discuss from this section is then, okay, what if I have frame-like Fourier expansions and I know my coefficients come from operator orbits? Can I classify all measures with this property? Okay, so the first thing you might be wondering is why do we care about these types of coefficients? So it turns out there are a lot of mathematicians that study frames of this form, frames that come from operator orbits. They have lots of nice properties. The first one that I think a lot of mathematicians are really think is really nice is that these types of frames tend to be really highly robust and forgiving as far as signal recovery is concerned. So, in a lot of problems with frames, you have a signal and you try to recover it from your frame data. And in real life, a lot of times you have noise and you have loss of some of this data. And so it's often desirable in application to have a frame with a lot of excess, where if I remove a lot of vectors from my frame, I can still have a frame. There are these frames called Carlson frames that are very, very good at this sort of thing. They're very, very redundant, and they're very good at being frames when you remove lots of vectors from them. They are of this form. But for the sake of this talk, the reason I like frames with this property is they kind of preserve the dual frame property in some sense, where there's a dual frame that's also of this form. So there's a dual frame where every element of my Hilbert space can be reproduced against a dual frame that's also an operator orbit. And that's going to come in handy for answering the main question of this section. Okay, so what this result says is that if we assume the coefficients are a frame, if I have frame-like expansions and the coefficients are an operator orbit frame, then yes, we can classify all measures that have this property. And so it turns out that my measure basically has to be Legbe measure. It has to be absolutely continuous, and the weight has to be bounded above and below on its support. So the converse of this statement is pretty easy to show. What this statement basically says is that's all you could have done. With these types of expansions, these are actually true Fourier frame expansions always, it turns out, when we further assume the sequence is a frame. Okay. So we classified the frame place completely. So to kind of walk you through why this works a little bit is we have this expansion with, operator orbits on the inside and the outside. And so it's pretty easy to show that because I have these two operator orbits, they better be the same operator. And so my operator T better also be multiplication by the exponentials. And a bit trickier to show is that mu is absolutely continuous, but can be done. And then I know my operator orbit is of this form in step 3 because of step 1. And I have an absolutely continuous measure where this operator orbit is a frame, and then it's pretty easy to show that the exponentials have to be a frame. And then I'm back to the case of the classification theorem of He, which says I know exactly what measures have a frame of exponential functions, and so I'm done. I have my classification in this case. So what's interesting about this argument, though, is it allowed me to take this question and transform this question into studying a question about classic Fourier series in weighted norms. And once I showed these two questions are equivalent, it was a really big hurdle for making leeway and understanding this question. So this question is equivalent to asking what absolutely continuous measures, what absolutely continuous measures have weights that sort of respect classic Fourier sums. I know there's an indicator function here, but don't worry too much about this right now. But sort of what weights respect classic Fourier sums is equivalent to this question we have in this section of the talk. And as you may imagine, this question has been studied a lot of mathematicians over the years. So let's think about this question a little bit here. So again, what weights respect classic Fourier sums? Do they have to be bounded above and below? Do I have to have equivalent norms to have convergence of my classic Fourier sums? And I think rather surprisingly, the answer is no. So for example, if we take weight 1 over square root of x, which is unbounded, this weight still respects classic Fourier sums, where I still have convergence in this weighted norm. Okay. So what's going on here? Well, what's going on here is this neat result due to Hunt, Muckenhau, and Whedon, where they classified exactly what weights respect classic Fourier sums. Right? It says a weight has weighted convergence of classic Fourier series if and only if the weight satisfies something called the A2 condition. Okay. And it turns out that 1 over square root of x may not be bounded, but it satisfies this A2 condition. So let me try to give us an idea of what is the A2 condition here. So basically a weight rather satisfies the A2 condition if it's essentially weakly bounded above and below. Or more precisely, it's like saying the average value of f and the average value of its reciprocal are control each other uniformly on intervals. So there's the formal inequality right there. But again, you can think of this as a weaker notion of being bounded above and below. So if anybody in the audience is, like I said, bored sometime and you'd like to check, if you have a power function with power in between -1 and 1, it will satisfy the A2 condition even if it's not bounded. Okay, but again, anybody's welcome to think of this for the sake of this talk as a weaker notion of being bounded above and below. Also, I can't give a good intuition why this is called A2 because the answer is it's exactly the weights that makes an operator strong 2, 2. So unfortunately, the name is not very helpful for the sake of this talk, but let's stick with weak notion of bounded above and below. Okay, so because of the theorem of Hunt, Muckenhau, and Whedon, I have that for the weight 1 over square root of x, my classic Fourier sums converge to all my functions in weighted norm. So to put that into mu world, I put a square root of x here in the coefficients. So what's going on here? Why is this not contradicting the theorem that I showed earlier? Well, it's because this sequence is not a frame anymore. So what that classification result I said earlier says is that if the coefficients are a frame, actually you're doing true Fourier frame expansions. But if not, like this expansion here is a frame-like expansion and more interesting stuff can happen. Okay, so that leads me to my conjecture about this statement here. So the main question of this section, can we classify all measures that have frame-like expansion with coefficients coming from operator orbits? So my conjecture is I think something similar is happening to the result of Hunt, Muckenhau, and Whedon. I think that these measures need to be absolutely continuous and they need to satisfy a type of weak A2 condition. So I realize a lot of mathematicians have a lot of different definitions of what they mean by conjecture. So let me just say, when I say conjecture here, what I mean is I believe this conjecture is true. I believe I have some good evidence to prove it, and I unfortunately have not been able to prove it yet. So again, if anybody has any ideas, I'd love to hear them at the end of the talk. Okay, so what is a weak A2 condition? Well, it's just the A2 condition, but I only need to check intervals that intersect where my function is positive, is what I think condition is going on here with this conjecture here. So it's a weakening of A2 because I only have to check intervals that intersect the x where my function is positive. Okay, so what kind of functions satisfy the weak A2 condition? Well, of course, if a function satisfies the A2 condition, it's going to satisfy this weak A2 condition. And then if I have a function that's bounded above and below where it's positive, it will satisfy this weak A2 condition because the weak A2 condition doesn't care what's happening when the function vanishes. So this led me to asking this question, is okay, if I have a weak A2 function, can I extend it to be an A2 function? Can I take the parts where my function vanished and change it to another function that's in A2? Because if I can do that, I can apply the results of Hunt, Muckenhau, and Whedon, and I could actually put this conjecture to bed. But of course, because this is a conjecture, sadly, the answer to this question is not always. You cannot always take a weak A2 function and extend this to an A2 function. But sometimes you can. For example, like I said, functions that are bounded above and below where they are positive, they're not only in weak A2, but they can be extended to be an A2. And I think that's pretty easy to see with kind of an illustration here. So I know I kind of mixed colors here, but the function in purple here, this is my weak A2 function. So it's bounded above and below. It vanishes. It's bounded above and below again, and then vanishes. Well, I can extend this to an A2 function by just copying the function where it's positive and then bumping it up to 1 where it vanishes. And now my function in red is bounded above and below, and so it satisfies the A2 condition. So functions like this can be extended. And then another example of functions that can be extended is if I have a function that's a2 on an interval and then vanishes. This can also be extended. What I want to point out here quickly is that it's not clear how to do this, because I think initially one might think, okay, all I have to do is pick my favorite a2 function and glue them together, and I'll have another a2 function. But it turns out it's not exactly clear that new function will be an a2, that the whole function's average values would be controlled by the reciprocals on the whole interval. But it turns out that one exists, and there is an extension for this. And that's due to a extension result that I came across by Kirky and Mandara, which in our case says this. It says that if my zero set of my function is not too bad, then weak a2 functions have a2 extensions. So what I mean by not too bad is I mean that it's a closed set modulo sets of Lebesgue measure 0. And this is good for us because it means that we can apply the theorem of Hunt, Muckenhau, and Whedon to get these expansions. Okay, so what I want to close this section off with is I want to say why I believe this conjecture is true. Like, what evidence do I have? Okay, so again, the main question is, what measures have frame-like Fourier expansions with coefficients coming from operator orbits? Conjecture is that measures that are absolutely continuous and satisfy that weak a2 condition. Okay, so one of the pieces of evidence I have is one direction I have proven. So if a measure has this frame-like expansion property, it's definitely absolutely continuous and satisfies the weak a2 condition. It's the other direction that I have not been able to nail down yet. So if a measure has a weight with this property, can we have these frame-like expansions is what I'm still trying to nail down. But what that a2 extension theorem was talking about, that's why we were talking so much about a2 theory, is that if my zero set of my weight is not too bad, if it's closed, my function has an a2 extension, and I can apply the theorem of Hunt, Muckenhau, and Whedon, and I have the converse. So in a case where my weight is, not too bad, I mean, if my weight is certainly analytic, it has this property, but it's really nothing about the function being smooth. It's just the function has a nice zero set. But the last thing I want to point out for why I think this conjecture is true is I think my extension theorem is pretty tight. And I'm not proposing that I think these weak a2 functions always have a2 extensions. But I also think, looking at what this question is asking, I don't think that's necessary. At the beginning of this section, I said that there is this indicator function and to not worry about it. Well, what that indicator function and the partial sum suggests to me is that the extensions of these weights sort of shouldn't matter, and it only should matter what's happening where these weights are positive. So I'm thinking that only this weak a2 condition is necessary for these expansions. But again, if anybody has any thoughts, feel free to let me know. So what I want to do to close this talk is I want to talk about a general condition for frame-like expansions, and hopefully kind of illustrate an idea of how can we feel overall about what's happening with these Fourier frame-like expansions. Okay, so it says that if I have a Fourier frame-like expansion, that's all this is saying here, with the upper frame bound, it's just saying my coefficients are square summable. What this says is I fall into one of two categories if I have Fourier frame-like expansions. So the first one is that my measure is absolutely continuous, it's bounded below, and it satisfies the a2 condition, and the sequence G sub n is minimally complete. So all of the information from the G sub n is extremely rigid and important. It's just like an orthonormal basis. So if I remove any of the G sub n from the sequence, my sequence is no longer complete. So all of my data is sort of very important. And the second case is G sub n has infinite excess. So I can remove infinitely many vectors from my G sub n and still have a complete sequence. So I like to call this all or no excess theorem, because what it says is that if we have frame-like Fourier expansions, it's not possible for my G sub n sequence to have finite positive excess. It either has no excess or it has infinite excess. Okay. So another way to kind of think about what's going on with Fourier frame-like expansions, again, is we have two cases. In the first case, we're doing classic Fourier expansions and we have no redundancy. All of my Fourier data is very, very rigid and important. But in case two, my Fourier expansions are extremely not unique. So if we think about the toy example where I drew the step function, and I drew my poorly drawn squiggles of the Fourier approximation, you can imagine that the way we did that was extremely not unique. We could have chosen other step functions. We could have done something with Lagrange polynomials or something. So we were in case two with that toy example. So this result sounds really, really impressive, maybe. It sounds like I'm saying, we have a complete classification of all measures that have frame-like expansions. But really, what I'm saying here is, yes, we have a complete classification of case one. We know exactly what happens when the expansions are unique. That's when I'm absolutely continuous, and my weight is bounded below with the A2 condition. But case two is the really interesting case that's hard to classify, and it's the case that many are still studying, including myself. But hopefully, this just gives an idea of what's going on with these frame-like expansions as a whole, with this all or no excess theorem. But here are some of the references that I mentioned. If anybody would like to see, they can let me know. And here's the paper on arXiv. And that's all I have. Thank you for listening.
All right. Thanks so much, Chad. I encourage everyone to smash the reaction button to show our appreciation for that nice talk. And if there are any questions, now would be the time.